Hi everyone, this is Dr. E. Sridevi, Professor, Department of Electronics and Communication Engineering. In this video lecture, we are going to learn about boundary conditions between two perfect dielectrics. On completion of this module, the learners can be able to understand the basis of and boundary conditions between two perfect dielectrics. So boundary conditions between two perfect dielectrics. Before that, we have to consider some conditions. Consider two boundaries between two perfect dielectrics. One has permittivity epsilon 1, another one is epsilon 2. And E and D have two components, tangential to the boundary and normal to the surface. And consider two boundaries between two perfect dielectrics. One has permittivity epsilon 1 and another one is epsilon 2. So two components E and D we said, one is tangential to the boundary and normal to the surface. So considering a closed path ABCD, rectangular in shape having the height del h and width del w, integral closed integral E dot dl equal to 0. So dielectric boundary condition this one. So E tangential 1 E E tan 1 plus E tan 2 plus etc. up to E nan 1 plus E nan 2 is equal to normal 2 is equal to 0. So total electric field in region 1 is E1, total electric field in region 2 is E2. So E1 N1 N equal to E2 N, that is equal to modulus E1 N equal to E1 N and E2 N equal to E2 N. So substituting this one and getting that value, E tan 1 equal to E tan 2, that is E tan 1 minus E tan 2 equal to 0. So the tangential component of medium 1 is equal to tangential component of medium 2. Thus the tangential component of electric field intensity at boundary in both dielectrics remain the same. That is, the electric field intensity is continuous across the boundary. So the statement of the first condition is electric field intensity is continuous across the surface. D equal to epsilon E. So D tan 1 equal to epsilon 1 E tan 1, D tan 2 equal to epsilon 2 D tan 2. So D tan 1 not equal to D tan 2. Thus, the tangential components of D undergoes some change across the interface. Hence, tangential D is said to be continuous across the boundary. So, normal conditions using Gauss law to find normal components. Closed integral d dot ds is equal to q into q enclosed. Closed integral d dot ds is equal to q into enclosed. That is, as del h tends to 0, closed integral d dot ds is equal to dn1 into del s, and similarly dn2 into del s, that is equal to q enclosed. So q enclosed is equal to rho s into del s. For top surface, the direction of d and n is entering the boundary. So bottom surface of direction d and n is leaving the boundary. So both are opposite in the direction at the boundary. Hence dn1 minus dn2 is equal to rho s. Hence there is no free charge available in the perfect dielectric. All the charges in dielectric are bounded to charges and are not free. Hence rho into s is equal to 0. So dn1 minus dn2 is equal to 0. So dn1 is equal to epsilon 1 e n1, dn2 is equal to epsilon 2 e n2. Refraction at the boundary. So dn1 is equal to d1 cos theta 1, dn2 equal to d2 cos theta 2. Referring this, now the boundary conditions become dn1 is equal to dn2. Hence d tan 1 divided by d tan 2 is equal to epsilon 1 divided by epsilon 2. Hence by simplifying and getting law of refraction, E and D at dielectric boundary, epsilon 1 is greater than epsilon 2, then theta 1 is greater than theta 2. Similarly for E2 square is equal to E1 cos theta 1 square plus E tan 2 square. D is larger in the region of larger permittivity. Hence E is larger in the region of smaller permittivity. So the applications of this electric boundary conditions are, it is used for capacitor design and it is used for dielectric material and analysis, and it is also for electrostatic field mapping and boundary value problems. So overall the electric conditions are based upon tangential and normal components, E tangential and E normal, E tan 1 and E tan 2, D tan 1 and D tan 2. Relating this all is based upon this this components, and similarly E normal 1 and E normal 2, D normal 1 and D normal 2 all are related with this one. So these all are the applications, and mainly it is used for solving boundary value problems. Hope you all listen this. Thank you for watching.